we have the meeting. So we are based in Trieste. This is, I think, a nice photo of part of our town center. And we're always very happy to host scientists that are interested in collaborating with us and that are interested in coming also to our laboratories for STSMs. So, you know, it could be an opportunity for those of you that would like to do that. And the work that I'm presenting today, very briefly, I'm very happy because it's, we just recently published it, and it's a fruit of a collaboration with the group of Juan Villatela at Midea Materials in Spain, and it happened thanks to an STSM that was funded by COST. So the activities of our group relevant to this construction are mainly on the covalent functionalization of carbon nanomaterials. And as I mentioned in the past, it's really a balancing act because you need to compromise between the properties of the pristine versus the functionalized materials. So I won't go into detail, but we reviewed the topic quite recently, and there you can find more about that if that interests you. And so for this work, we decided to functionalize the carbon nanotube fibers, which is this kind of material that is produced in Spain by Juan's group. And I think you will hear more about this material in the afternoon. There will be a talk by another Juan. And this kind of macroscopic material is actually made by carbon nanotubes. So you may think that, okay, the kind of approaches that you use to functionalize covalently carbon nanotubes in dispersions can easily be applied also on this kind of macroscopic material. However, to make the story short, actually that's, it's not a good idea, as Yoda is suggesting here, we're shaking his head, because you really ruin, with the typical liquid-based functionalization methods, you ruin the macroscopic morphology of the carbon nanotube fiber. So you can get the functionalization going, but if you're interested in really the morphology of the macroscopic material, then it's a problem. However, we decided to turn to the light, and then things got working. So in this case, we used this very convenient and portable piece of equipment, which has simply a very powerful UV light inside with two different wavelengths, one at 185 nanometers and the other one at 254. So what it does is that it produces ozone from oxygen that is contained in the air. You don't need any compressed gas cylinder or anything particularly fancy. And then you produce radicals from that, and of course the UV light gets absorbed by small molecules, or if your substrate has organic material, as was our case. So in this manner, here you have a vial with a biphasic system, and you can see that the pristine fiber was really hydrophobic and went into the toluene, but after the functionalization went into water. And this was used by our collaborators in Spain to prepare all solid flexible supercapacitors, and also for the electrochemical characterization and the mechanical characterization. You can find more details on our joint publication here. So there are many advantages for this kind of functionalization, and of course we can apply it also to different kind of carbon nanomaterials if you're interested. If you compare it, for instance, to the typical oxidation procedures that are liquid-based, you don't have to worry about purification, you don't have to use chemicals or solvents, no purification steps, no waste produced or to deal with, no solid or liquid waste. So it's very convenient. And also the equipment is small, so it can easily be carried around if you need to do the functionalization next to another piece of equipment for some other analysis. And we have characterized the material by a number of different techniques. Here I'm just showing that SEM still shows the presence of the tubes. By high resolution TEM, you can see that actually as you progress with the functionalization, you do introduce defects into the sides of the nanotubes as expected. And this was applied to two different kinds of carbon nanotube fiber produced from butanol as a precursor or from toluene as a precursor. The two fibers have different levels of pre-existing defects. And this means that these ones are more reactive And these ones are a little bit less reactive, but you can still oxidize them eventually. And so you can fine-tune the level of oxidation depending simply on the reaction time that so basically the time that your substrate stays in contact with the high energy UV. And in each case, the functionalization was monitored for over 3 weeks, and it was pretty stable. So this was just a quick concept to give you an idea of the kind of activities that we do, and we hope there will be more STSM of this kind. This is our group in Trieste. These are other funding agents. And Daniel is the PhD student, now a postdoc in my group, who led this work. And these are our collaborators at IMDEA in Spain. And of course, thanks to COST for funding the STSM. And thanks to you for your attention.